everyone. My name is Dr. Steve Black. I'm a pediatric infectious disease specialist and professor of pediatrics at the Center for Global Health in Cincinnati Children's Hospital in Cincinnati, Ohio, in the United States. And today I'm going to be talking to you about correlates of protection for vaccination. This is a disclaimer I'm required to insert. So what is a correlate of protection? And as we'll see, we'll also go through why are we talking about that and why they're important. A correlate of protection is a clinical measure associated with protection against infection in an individual or population. And that sounds a little bit complicated, but we'll go through it here piece by piece. Population correlates are based on a measure which is usually an antibody titer which is associated with a given level of protection in the population as a whole. Now, note this is not 100%, and it's usually not usually 100%. In fact, most often, 50% protection is targeted, not because that's the public health target, but because statistically that's usually the easiest to describe. So again, the correlate would be a level of antibody that is associated with, for example, 50% protection in the population. An individual correlate of protection is different. It's the amount of antibody associated with protection against disease in an individual. For example, a rubella titer of greater than 1 to 8 is associated with immunity to that disease. In fact, this is really also a surrogate of protection. It's a stronger measure that absolutely substitutes for effectiveness. That is, if you have this level of antibody, then one is protected. So all surrogates correlate with protection, but not all correlates are surrogates. Now, why are these useful? Well, it's useful for the development of vaccines against some diseases, such as meningococcal disease, for example, where the performance of a trial is not feasible. For this disease, the disease is so rare that a trial logistically could not be accomplished. It's ideal if you're going to take this approach if a correlate is available from prior studies. We'll talk about how those might be derived in a bit. For the evaluation of a new iteration of a vaccine, correlates are also useful. And the best example here is influenza vaccine, which, if you think about it, is a new vaccine every year. It has new antigens, it's composed differently, and it's different than the prior year's vaccines. So since the time frame between when the vaccine is developed and when we need to use it is usually measured in months, really there's not enough time to conduct a trial to evaluate the efficacy, so an antibody measure is used. Additionally, in new iterations of a vaccine, for example, in going from a 7-valent to a 13-valent conjugate vaccine, a correlate of protection was used to compare with the benchmark 7-valent vaccine, for which an efficacy trial had been done. So how do you assess a correlate of protection, now that we see that they're useful? One way that's the most direct and easiest to understand is a challenge study. And what's done here is you take individuals, you vaccinate them, and then at a fixed time later, usually 1 month, you challenge them with the infection. The amount of virus in the challenge is well controlled. The time of challenge is well controlled. So it's relatively easy, as you can see from this red arrow on the chart, 1 month following vaccination, to assess the correlate of protection at that point in time. What's done, if you're looking for something that correlates with 50% protection, for example, is to look at the antibody titer that's associated with half the individuals being infected after challenge and half the individuals not. So while logistically this sounds straightforward, obviously this is only applicable in diseases of minimal risk, such as influenza in healthy individuals, but not for Ebola, which could potentially be life-threatening. The other way to obtain a correlate of protection is from a clinical trial. And in this situation, it's much more complicated. You usually have a large population of individuals. You have antibody assessments on some or all of them. And however, when the individual gets exposed to the infection really is not up to you. It could be a very short time after vaccination, as is shown here, or it could be a very long time later. And also the inoculum or amount of bacteria or virus that they're exposed to is well beyond your control. However, this much more closely mimics real world or real life conditions. So what about the history of correlates of protection for influenza, since this is where this concept is most frequently used every year? So the initial development of a correlate of protection against influenza was by Hobson in the early 1970s. And he challenged healthy young adults with 10 to the 5th to 10 to the 6th egg infectious doses of influenza virus. And the correlate was defined as the level of HIA, or hemoglobination inhibition antibody, that was associated with 50% protection when the individuals were challenged here 2 weeks after vaccination. And he determined the level of antibody to be 1 to 40. Now, even though this was only for one specific influenza type and was only in healthy young adults, and was only for 50% protection, this titer has been used subsequently as a licensing criteria for influenza vaccines each year. Interestingly, Fox and others performed an epidemiologic study in Seattle in the 1970s evaluating this correlate and stated that the appropriate correlate in children was probably at least 1 to 80 or perhaps higher. And as we know, influenza vaccination especially targets elderly individuals, and they've not been assessed in challenge models at all. So we really don't know how much antibody might be required for 50% protection in that population either. So just from this one study, influenza licensure policy has followed over the last 40 years. Now, correlates are usually developed from a clinical trial, as I said. So I'm going to go through an example here. And one example is this paper, which is based on a trial from Timo Vesikari, who's an investigator in Finland. It was published in the New England Journal of Medicine. And this is a trial that evaluated adjuvanted seasonal influenza vaccine in children 6 to 72 months of age. It actually involved more than one vaccine, as we'll see. So this is a comparative study. It was conducted in Finland and Germany over a 2-year period. And about almost 5,000 influenza-naive children were vaccinated and randomized to receive 2 doses of adjuvanted influenza vaccine, unadjuvanted influenza vaccine called TIV here, or a control vaccine in the sense of placebo. In year 2, there were 800 vaccinees who provided pre and post blood samples, and that's what allowed the correlate to be calculated here. And children were followed with respiratory illness. Those individuals had swabs for PCR testing for influenza. So this is what the diagram of the trial looks like, but that's basically what I just described to you. There are 2 doses because that's what's routinely recommended in young children, and there were 2 years, and actually 2 different control vaccines. So this is what they found. This shows you the adjuvanted, the unadjuvanted vaccine, and this is both the efficacy for both of them is versus the control. You can see the adjuvanted vaccine was twice as effective, 86% versus 43% versus the unadjuvanted vaccine. Now, what you can see here is if we compare the antibody titers to the efficacy at the bottom, and the percent above the immune correlate of 1 to 40 in children shown here. Sorry, should have brought water to this session. You can see that the percent with a titer greater than 1 to 40 overestimates the efficacy in both vaccine groups. The efficacy was 45% in the unadjuvanted group but 65% of children achieved the 1 to 40 titer. And the efficacy was 89% in the adjuvanted group, and virtually everybody achieved the 1 to 40 titer in the adjuvanted population. Now this is a type of graph that's very useful in beginning to think about this. It's called the reverse cumulative distribution curve. And this shows the HI antibody titer by vaccine group, the adjuvanted, unadjuvanted, and control group. And it shows the cumulative proportion of children who received an individual antibody titer. You can see here for 1 to 20, virtually, and even 1 to 40, which is in the middle here, virtually everyone in the adjuvanted group, as we saw, got that. Really only about half the individuals in the unadjuvanted group, and about 20% in the control group. And if you look at higher titers, you can see the groups diverge even more. And you can begin to see here that what's associated with about 50% protection in the children is really quite a high antibody titer. So, looking at this data, we decided we would try and calculate a correlate of protection in children. Now, in order to do this, you need to look at the Prentice criteria. And this criteria requires that the observed vaccine effect can be explained in a statistical model using the immunologic data alone. That is, whether you're in the control group, in the unadjuvanted group, in the adjuvanted group, if you have a given titer, that will predict whether you're susceptible or not. So it doesn't matter which vaccine group you're in. It's only the amount of antibody that you have that determines your risk. But you need to assess that first, otherwise you can't estimate a correlate. And this is the statistical explanation of what was done, and indeed we're able to fit a logistic regression model that only included the antibody titer, and that predicted for whether children were getting disease or not. So now that we met the Prentice criteria, we then went on to try and define a correlate of protection in children. And the model of Dunning was then used to estimate that again using logistic regression and statistical model. So what happened after all that mumbo-jumbo about statistical models? They're important, but they're really just a tool to try and come up with these results. And what we see here is that the amount of antibody in these children required to provide 50% protection is more than twice what's required in adults, 1 to 110 titer. And if you wanted to target a reasonable public health measure, for example, 80% protection, because we really don't vaccinate children to only protect 50%, you need a titer of 1 to 330. Now, again, we talked at the beginning about individual versus population-based correlates. The numbers I just showed you here are for the whole population in the clinical trial. Whereas if you look at individuals, you can see that some individuals with low titers were protected, whereas some individuals with very high titers got sick. Now, why is that? Well, the reason for that is one, they may have been exposed to a large amount of virus. They may have had other predisposing conditions. We really don't know for the individual. So this titer we just spoke of here does not predict for individual protection, but for the population. So please keep that in mind. Now, the other thing to think about is that the amount of antibody required for protection varies depending on the time of exposure. Remember, in the challenge model, we knew when they were going to be challenged, whereas again, in the real world flu season, some of the children who were vaccine failures could have been exposed way out here when their antibodies have fallen off, because you get vaccinated here, and right after that, after your peak antibodies, your levels fall off with time. So one other thing we tried to do is at the time these children got sick, we tried to estimate using the exponential decay curve I showed you here, how much antibody was required at the time of exposure. And again, at the time of exposure, a 1 to 85 titer was, we estimated, was required for 50% protection. And again, a titer of about more than 1 to 300 was required for 80% protection. So in summary, the use of this standard 1 to 40 protective correlate for children really is not appropriate. We wouldn't have known this unless we developed our specific correlative protection for these children. And for public health purposes, we need much more immunogenic vaccines in children and adults. So correlates are useful. We're seeing they're useful for influenza. They're useful for adding new serotypes or components to existing vaccines. They're useful for rare diseases. And you need to go through a pretty rigid statistical process to really define the correlates for them to be of use. The correlates are only useful for the specific strain and the specific age population for which you develop them. But even really this is an simplification. It really only works for some diseases. All correlates that are in current use employ antibody titers. I'm sorry. Antibodies are easy to measure. Protection has been largely mediated by antibodies alone for most vaccines that are in current use. But for other diseases, including CMV, HSV, TB, and for that matter, varicella, where protection is mediated partly or largely by cellular immunity, this antibody correlate approach we described earlier will not work. And for these diseases and vaccines, it may be necessary to use a correlate involving cellular immunity or to use a complex correlate that involves both antibody and cellular measures. And I just refer you to this publication by Stan Plotkin in Vaccine that reviews these concepts in more detail. So complex correlates can include both CD4 and CD8 T-cell responses. They're responsible for controlling and terminating influenza infection, and may be a better correlate for heterotypic, that is, against different strain protection. For pertussis, there is no single antibody correlate, and a combination of different antibodies or cellular correlates may be required to assess prevention and protection against this disease. And that's especially important given our current issues with prevention of pertussis. For Ebola, antibody is required for protection, we know that, but is not effective in the absence of concomitant T-cell response. So then would dictate that we probably need a more complex correlate there. And for malaria, a study of T-cells after vaccination showed that effector central memory CD4 T-cells were required, along with other factors, to predict infection. So this malaria is quite complex. So let's look at another example here. We looked at influenza, which is actually pretty straightforward. For invasive influenza disease, I conducted a trial of a 7-valent vaccine in children in California, in which there was data available from more than 37,000 children, and immunogenicity in a subset of 229 children. Importantly, there were no cases of invasive disease in this immunologic subset, but that doesn't mean you can't calculate a correlate. As long as this is a random sample of a larger group, you can use the antibodies from here and the results for efficacy here to still calculate a correlate. And in this trial, the efficacy against invasive disease was 98%. And what you see here is something that's pretty complicated. These are the antibody responses in the control group. These are the antibody responses in the immunized group. But unlike influenza, there's not one line here, because this is a 7-valent or 7-component vaccine, and it's really a combination vaccine. Each serotype, each pneumococcal serotype, develops a different antibody curve, and actually you could, if you had enough cases, calculate a correlate for each serotype separately. What was done here, however, was to look at separating these two curves, where all the cases virtually occurred. These curves, where none of the cases occurred, you can see that for an antibody level of about 0.15 to 0.5, that separates these two groups. So that was chosen, this 0.15 actually, which you could argue maybe that was too low, was chosen as the correlate of protection overall. The reason why was that done? It was done to allow introduction of higher valent vaccines for which an efficacy trial was no longer feasible. And again, this is just to demonstrate that for the antibody responses for each serotype were pretty specific. As you can see that this is separated here at about 0.15. Meningococcal B is another example why correlates are useful, but also complicated. Bexsero brand is a 4-antigenic component vaccine. All of the components can be active in preventing disease. One correlate will not work because not all meningococcal B bacteria have all the antigens expressed. Some can have none. Some can have 1, 2, 3, or 4. If the organism has all 4 antigens, it's likely that a lower level of antibody will protect, since you have 4 different modalities of protection. So this has required a very complicated approach, which is even further complicated by the fact that it's not logistically feasible to perform a clinical efficacy trial here. Group B strep is another example. This is even more complicated. Group B strep is a major cause of infection in newborns, and it should say very young, not very young, not very long infants. It has 2 forms, early onset, late onset, and it's usually acquired from the mother at about the time of birth. So that means it's not possible really to immunize the infant, but nonetheless there's a high level of need here because the morbidity and mortality are very high in these young infants. So the approach that's been taken, since the infant is too young to vaccinate directly, it's proposed to vaccinate pregnant women, allow passive transfer of antibody to the baby, to the fetus, and then after the baby is born, this will provide protection. So the question then becomes, what level of antibody in the mother will protect infants against early onset disease, which occurs very early on here, and against late onset disease, which largely occurs out here. So you really would have 2 correlates if you think about it. One is for early onset disease, where there's more antibody, but since the antibody falls off with time, you'd have another correlate of what's required out here. And remember, what we're measuring is the amount of antibody the mother develops, and then that gets transferred to the fetus before it's born. The baby is born with a certain amount of antibody, then it decays here. So what we're measuring in the mother is over here off the slide someplace, is removed really from what effect we're looking for in the baby. So correlates, in summary, are useful for licensing new vaccines. Defining and using a correlate requires understanding the pathophysiology for one, but also requires meeting strict predefined statistical criteria. And correlates can be complex if both B and T cell responses are key for maternal immunization, as we've seen, and for multiple component vaccines. But even for a simple correlate for influenza, I think we've seen it's important to understand that they only apply for a given vaccine strain and only for a specific age group. So thank you very much for listening. I'm sorry that I can't take any questions here, but you can email me if you would like, and I'd be trying to answer your questions if you have. Thank you very much.